Okay, Calc Kids, this is now section 1.6, which is the last section of the chapter. Homework assignment up here, page 130, and this is mathematical modeling. So we are dealing with things called variation and like basically the way that variables relate to each other, okay? There's four main types of variation. The first one is direct variation, so I'm going to have you label these. One is direct variation, and then they have kind of a little step further on direct variation to the nth power, but we'll get to that, but it's still under direct variation. Number two, the different type of variation is called inverse variation. On the back side, we do combined variation, and then the last one is joint variation. So those four are the main types of variation, okay? And they're just the way that variables are relating to each other, okay? So there are two basic types of linear models. The more general model has a y-intercept that's non-zero. Okay, don't worry about that. Simpler model, y equals kx, okay? This is the skeleton or the main like representation of direct variation, okay? Y equals kx, I'm going to write that down here. Y equals kx. If two variables are directly related to each other, like y and x, they will be like y is equal to some number, which is what k is, times x. That's a direct relationship between the two, okay? And the verbiage that they will use when they're talking about this is they will say y varies directly as x, or y is directly proportional to x, or y equals kx for some non-zero constant k. All of those things mean that you're starting with something that looks like y equals kx. Now, when you do the homework assignment or something like that, and even down below here in this example, they might not use y and x. They might say like z and w or whatever, but you'll just replace those with the y and the x in this spot, you know, that type of thing, okay? So k is called a constant of variation, and in direct variation, inverse variation, we will all of those four different types of variation, each one of them will have a constant called k, okay? So that's kind of how that works. So y equals k times x, that's a direct variation equation, all right? So here's my example. In Pennsylvania, the state income tax is directly proportionate to gross income. So here's another example of where they don't use y and x. They use state income tax is, and the word is means equals, directly proportionate to gross income. So I'm going to say tax is equal to something times income, right? And I'm going to use the letter K to represent that. So tax is directly proportionate to the gross income. We just have to figure out what K is. And K, in this case, is going to be your tax rate, right? Like you take your income, you multiply by the tax rate, and that tells you how many taxes you pay, okay? So that's kind of how that works, all right? You are working in Pennsylvania, and your state income tax deduction is $46.05. And that's your state income tax, okay? For a gross monthly income of $1,500. Find a mathematical model that gives the Pennsylvania state income tax in terms of gross income. Well, we've already kind of found that model. This is the model, except we need to figure out what the tax rate is. We need to figure out what K is. So all we do is we use these numbers to solve for K. All right, so the tax rate was $46.05, and that's equal to whatever that rate is times 1,500, because that was my income. And all I do is divide by 1,500, and we will see that, I gotta use my calculator here, 4602, or 05, 4605, divided by 1,500, and that is 0.03, yeah, we'll just go 0.03. So K, in this case, equals 0.03, so it's like a 3% tax. And our mathematical model for that is going to be the amount of taxes you pay is 0.03 times your income. And that's our mathematical model that we need, okay? Now down here they have direct variation as an nth power, and they say, you know, this is one really good example, is that area of a circle is pi r squared. Now the variables that I have going on here in area equals pi r squared is area and the radius, right? Those are two variables, and they are still directly related to each other, where k is the value of pi, but we have to take the radius and square it first, okay? So they're still directly related to each other, but it's the variable squared first, okay? So this, so the verbiage that they will use is y varies directly as the nth power of x. They will say y is directly proportionate to the nth power of x, and they won't say nth power. They'll say like the 4th power of x, or the 3rd power, or the 7th power, or whatever, right? And what this is going to look like is y equals k times x to some power. All right, I'm going to write that really big here. Y equals k, x to the nth power, and again, n will have a number to it, so let's say the 3rd power or something like that. This is still, k is still going to be a number. K is still going to be a constant that you have, okay? So the distance a ball rolls down an inclined plane, okay, we're talking about distance, I'm going to underline that, is directly proportionate to the square of the time it rolls, okay? So distance is directly related to the square of the time, okay? So let's go over here. Distance is directly related, we know we need a constant in there, directly related to the time squared, and that's what our function is going to look like, okay? During the first second, so that's talking about time here, during the first second, when t equals 1, the ball rolls 8 feet. Our distance is 8, okay? So, in part A, so they say find a mathematical model that relates distance and time. Okay, so basically in part A, they're saying solve for k and tell me what the function is, all right? So, that's where we use t equals 1 and distance of 8. So, 8 equals k times 1 squared. And 1 squared is just 1, and 1 times k is 8, so that means k is 8. Okay, so our mathematical model will be that the distance is equal to 8 times t squared, and that's part A. That's what they're wanting for part A. Now, part B, they're using that formula to solve other things, right? How far will the ball roll during the first 3 seconds? So we just plug 3 in for t, and we solve for d. So d equals 8 times 3 squared. 3 squared is 9. 9 times 8 is 72, so the distance will be 72, and I think it's in feet. Yeah, feet, 72 feet, okay? That's how that works, all right? Now, we move on to the next type of variation, and it's called, oh, wait a second, before we move on, let's go to direct variation. Direct variation looks like this, in its main form, not as the nth power, but in its main form. This function right here will be a linear function. So direct variation will look like a linear equation. Y equals k times x is linear. It's just like this thing right here, because it's just saying like k would be your slope in that case. And I guess they did say that up here, linear model. Okay, y equals k times x, it will be a linear function. Okay, now if we move down here to inverse variation, an inverse function, the main equation for that, I'm touching things that I don't need to. Okay, main equation for that is y equals k over x. Okay, so like maybe y equals 1 over x, or y equals 7 over x, or something like that, right? And inverse variation, the graph of him will be those boomerangy things, right? Because 1 over x is this thing right here. This is inverse variation. Now, usually when you're dealing with story problems, you can't have like negative distance or negative time. So like these things over here don't matter, and you're just looking for like, it kind of looks like an exponential function. So really you're probably only looking at the top half of that boomerang. But it still will end up being, like the equation of a boomerang function, okay? And this is y varies inversely as x, or y is inversely proportionate to x, or y equals kx for some non-zero constant k. All of those things mean you're starting with a function that looks like this, okay? So let's go down to, oh, they don't give us an example of inverse variation. Okay, but we're going to skip down to 3 because combined variation incorporates inverse and direct variation at the same time. So combined variation is a combination of both direct and inverse variation in the same model. So combined variation is the first one that we will experience that operates with 3 variables. Okay, so let me give you an example of this, of how the equation works. They will say y varies directly with x and inversely with z. Okay, and what this equation is going to look like, a direct variation is y equals kx, that's direct variation. But inversely with z means that z is going on the bottom here now. Okay, so we still have that constant k, but it's using direct and inverse at the same time. So that's kind of how that will work, okay? An example of this is the pressure, the volume, pressure, temperature, gas law that you guys might have had in one of Mr. Moose's classes. But here is the example. A gas law states that volume of an enclosed gas varies directly as the temperature and inversely as the pressure. So we have volume, varies directly as temperature and inversely as pressure. Those are our three things, and we're going to go ahead and you can assign whatever variables you want to. So I'm going to say volume equals, we're varying directly as pressure, directly as temperature. So I'm going to say KT over P. And some people might not like to use T just because T is usually used to represent time, but as long as you know what you're doing, that's fine. Okay, you can use whatever variables you want. The pressure of a gas in 0.75 kilograms per square centimeter. Oh, I think this is supposed to say is. The pressure is 0.75 kilograms per square centimeter when the temperature is 294 Kelvin and the volume is 8,000, okay? Find a mathematical model. Again, this is just like saying find the K value and write me what the equation looks like, okay? And that's where we use these three numbers up here is to solve for K to begin with. Like, what is this constant? What is this number that never changes? If I'm given, any three other values. So 8,000 is going to go in for the volume. Temperature is 294. And pressure is going to be 0.75. And we're going to solve for that K, okay? So I'm going to kind of do this like 8,000. We would end up multiplying by 0.75 to the other side, right? Times 0.75. And then we would divide by 294 to get K. I hope that made sense. I kind of did that in a crammed space, but you're unwinding the equation, you're solving for K. So 8,000 times 0.75 divided by 294, and that K is going to be 20.4, let's say, if we round to one decimal place, 20.4. I hope I did that right. 294, let me do that again, times 0.75 divided by 294. Yep. Okay, so our constant is 20.4. So I'm going to write the mathematical model, which is all the way down here. Volume is equal to, that constant was 20.4 times the temperature over the pressure. And that's what they're wanting for part A. Now they're saying find the pressure when the temperature is 300 and the volume is 7,000, okay? All right, so the temperature's only slightly changed from 294 to 300, and the cubic centimeters only slightly changed from 8,000 to 7,000. I mean, that is a little bit of a change, but I always like to look at the information that was given to me because for pressure, if we're solving for pressure, the original pressure was 0.75. So I can anticipate that my new pressure is going to be a decimal number that's close to 0.75 or around that range. Like if I would get a number that's like in the hundreds, probably not, right? Kind of look at what seems to be a reasonable number. So find pressure, we're saying volume is 7,000 equals 20.4 times 300 all over P. And I don't know if you remember from doing this before, but 7,000 and the P can switch places with each other. So P is equal to 20.4 times 300 over 7,000. 7,000. And 20.4 times 300 divided by 7,000. And that is something like 0.87. So kind of what I anticipated. I said that was going to be a decimal. And the units on there, I just get from the units above. So that's kilograms per square centimeter. So kg per centimeter squared, or square centimeter. That's what my pressure will be, okay? Last one, joint variation. Joint variation is another one where we have three variables. Three variables. And joint variation, we'll say, like this one says z varies jointly as x and y. And what this looks like is that z equals k times x times y. It's kind of like direct variation, except you have two variables that have to join together to be directly related to z, okay? So that's why it's joint variation. Those two together have to make up what z is, okay? So z is jointly proportionate to x and y, z equals kxy for some non-zero constant k. And here's an example. The simple interest for a savings account, so interest is jointly proportionate to the time and the principal. Okay, so let's write out what that looks like. Interest is jointly proportionate, we need a constant in there, to the time and the principal that we're doing, okay? After 1 quarter, which is 3 months, that's a time equals 3 months. Maybe, we'll see what the units are in. The interest on a principal is 5,000. Oh, the interest on a principal of 5,000. Principal is 5,000. The interest is 43.75. Okay, and they're wanting us to find a mathematical model. So that's just saying, using this information, solve and tell me what the k is. Okay. And what we're going to do is when we do this, when we do anything that's involving time, since we only have one unit that involves time, we can choose whether we represent this number as a in months or in years or whatever we want to use it. Just like on part B, when we do after 3 quarters, we need to make sure we keep that same unit, okay? Now, if we had 2 units measures of time, like time was over here and time was over here, they would just have to be the same unit of measure. Like one, if we're gonna do in years, we need to stay in years, or if we're gonna do in months, we have to stay in months. But here we get to choose. Just as we answer the next questions, we have to make sure that our number stays the same. Our constant k is what will change depending on whether we have it in months or in years, okay? So it doesn't matter what our constant k is as long as we are consistent about plugging months in versus plugging years in, okay? So I hope that made sense, I hope. Anyway, so I'm going to leave it as 3 months, and then P is 5,000. So this together is 15,000, and I'm just going to divide 43.75 divided by, that's quite a large number, or I guess quite a small number. Blah, 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 3 months. Yep, that should be good. So our k in this case is a really, really, really small number, and I'm going to go 4 decimal places, 0.0029. So for part A, write a mathematical model is I equals 0.0029 TP, and that's what he will look like. Part B is saying find the interest after 3 quarters. Okay, so I'm solving for interest, and 0.0029 after 3 quarters. So 1 quarter was 3 months, so 3 quarters will be 9 months. Okay, I'm going to say 3 quarters equal 9 months if 1 quarter equals 3 months. I hope that makes sense. So I'm plugging 9 in, and then they don't tell me what my principal is, but we're assuming that we're using the same principal as the original problem. Okay, so all I have to do is multiply those guys together. So I'm going to take that number, and I still have that 0.0029 in my calculator, and it's not rounded off. So I'm just going to take that same number and times 9 and times 5,000. So if you're doing this on your calculator and you went ahead and rounded it off, that's fine. You might just end up with a different answer, like this 25 might be like 24 or something on yours. But I used the original value, okay? So those are the different types of variation. I hope that all kind of made sense a little bit. And, we didn't talk about the graphs of each one of these. Direct variation was linear. Inverse variation was those boomerangy functions. Combined and joint variation, because they involve 3 variables, these equations will be like 3-dimensional space, right? So these might be like functions that are existing or graphs of functions that exist in 3-dimensional space. So I'm not going to worry about the graphs on those so much. Really just inverse and direct are going to be linear, and these are called the reciprocal functions. Okay? But don't worry about the graph of combined and joint, okay?